Okay, so today the topic is two different things. So the first topic is fast gradient echo. So this is it's just like a real basic sequence. It's like when you go in the scanner, the very first thing you do is you need a quick and dirty image to find out where the head is, because you don't know where the head is, and you want to like set where your higher resolution images are. And so what is that? It's a fast gradient echo, and this is so we haven't talked about all the different parts of the pulse sequence, but we'll just draw it out. What's the motivation for this? The motivation is collecting the data quickly. Like if you want to just collect data in like 10 seconds in the scanner, and you need tens of thousands, hundreds of thousands of data points. If you're waiting around for sort of T1-like times, a couple seconds, and then recording a small burst of a couple hundred points, that's not going to do it. And so the idea is, how can we record hundreds of thousands of data points per second? And so that's what fast gradient echo is. And so so there's a bunch of different names for this, which you have to learn, because if you're reading anything, you'll just say, oh, it's a flash sequence. So sometimes this is called flash for a lot of these names. I don't even know exactly what they mean, but this one I know. It's fast low angle shot. So that's the principle of fast gradient echo, is to do a very small flip. That's the low angle part. But this one's sometimes called SPGR, and that stands for spoiled grass. And then what is grass? Well, grass was gradient echo something in the steady state. I can't remember what the A stands for. That's also another fast gradient echo method. We'll talk about that a week or two from now. And sometimes that second one, which is different than flash, different kind of thing, is called SSFP, which is steady state free precession, and sometimes it's called FISP. I can't remember what that one means, but it's got precession in it. So we'll just talk. The most generic one, I would say, is flash. So that's what we're going to describe, because it's sort of fast. And so what does it look like? It's a bunch of very rapid RF pulses and gradients. So here's the RF stim. That's what we're putting into the head, and we'll assume that we're in the steady state. So remember, we talked about you have to do a number of pulses before you get to the steady state. We're just assuming we're in the steady state. And so how does this pulse sequence work? There'll be alpha n minus 1. That's kind of like the last RF pulse. And here's the next RF pulse, alpha n. And how fast are those going? Well, quite fast. So those are going like about 100 or 200 per second. And the reason that the scanner makes a noise is because you're flipping all these gradients around. So so when you draw our pulse sequence diagram, we always have 5 lines in it. So this is the transverse signal, which is the one we're recording, the only one we can record with the RF coil. And then we've got the gradient. So here's the Z gradient and the Y gradient and the X gradient. And so how does this work? We'll pick out a slice. We'll explain later how that picks out a slice. And then we'll do some phase encoding. We haven't explained phase encoding yet, but that symbol means repeat this sequence with all the different settings of that gradient. So like do it like 256 times with 256 different settings of this gradient. And then this gradient here is the one that actually is on when we're reading out the data. And so what is the signal we get out? We get out an FID from that RF pulse, which we ignore. And then we've messed up the phase with this gradient right here, T2 star star. And then we unmess up the phase with this gradient, and you know the area here is supposed to be the same as the area here. And then in the middle of that gradient being on, we end up with a gradient echo. That was our not as morally upstanding echo, which was an echo that essentially results from messing up the phase and then unmessing up the phase. And then we get back to what would have happened if we hadn't done anything at all. And this, the curve describing the height of that is our, e to the minus t over t2 star. Because it's going to include effects of static offsets. We're not correcting it like we would if we did a spin echo. Okay, so that's our basic pulse sequence, and you can see these gradients are flipping back and forth, and if we're doing 200 a second, and then we didn't say like, what is the data we actually record? We don't record the FID. Here's the actual data that we digitize. Might digitize, like 256 points there. So this is, data. So why does the magnet make noise? Because this time here, this time is our TR. TR. For example, 7 milliseconds. So that means over 100 of these, and so TR. That means we're going to do another select here and another phase encode here and another one of these guys here, etc. So why does the magnet make noise? Well, you've got this gradient is turning from positive to negative like 150 times a second, and so that's what makes that sound, because it's just going back and forth hundreds of times. So you're collecting a lot of data. In 1 second you could collect 100,000 data points. So that's the fast gradient echo. So that's the sequence. And so what we want to do is figure out what is the basic equation that describes the amplitude of this echo. So that's what we want to find out, like how bright is that, because that's how bright the pixel is going to be. Okay, so if we look at point A, and point A is basically so we also have the longitudinal magnetization, which we can't see, right? We can't see. But what we're interested in is what is the longitudinal. The first equation is what is the longitudinal magnetization that is basically at this point here. And this point is right before the nth pulse. So we'll start off, our first equation is what is the longitudinal magnetization right before we do the next pulse, because that's going to describe how much signal we get out from this pulse, because that's how much has regrown, and so that determines our signal. So what's the driving force behind this pulse sequence, and what it is we're trying to do a low angle shot, meaning an RF stimulation. And so if we start off with, our MZ0 up here, if we do a 90, it's going to take like 4 or 5 seconds before we get our longitudinal magnetization completely back. So that's kind of a long time. But if instead we just do, say, like an 8 degree or a 10 degree, what's going to happen then is that we'll still get a reasonable, well, let's put the triangle this way, because you usually put like, the 0 is aligned with the Z. So we're still going to get, a reasonable amount of transverse. And what is that going to be? It's going to be basically, here's that angle. It's just going to be the sine of the angle. And then we're not going to kill too much of our longitudinal. So the longitudinal is going to be, if there's the right angle, that's going to be the adjacent, and the longitudinal is going to, equal cosine. So that's ML. And since, what cosine, cosine looks like that, and so as long as you keep your angle kind of low, like 5 or 10 degrees, you're hardly gonna hurt your longitudinal magnetization at all. But you're still going to get, a reasonable amount of transverse magnetization, maybe like a quarter as much as you would get if you did a 90. And so that's the basic principle here, is that what we want to do is kind of, save our longitudinal magnetization. And because we're doing such a good job of saving it, we can do 100 pulses a second instead of like, 1 pulse every 3 seconds. So we're going hundreds of times faster. So what are the equations? So the first equation is equation A, which is what is the magnetization, what's the Z magnetization, the longitudinal magnetization? So I got for the nth pulse right before. So right before the nth pulse. So that's the meaning of that. So that's this guy here. Z of the nth pulse, but right before it. And so what that's going to equal is going to equal our Bloch equation. So our Bloch equation is the equilibrium magnetization, proton density basically, and then the first times the first term, e to the minus time of repeat over T1, and then plus the starting condition, and the starting condition is essentially right here. So the starting condition is this guy, and that would be mz of the n minus 1th pulse right after the pulse. Okay. So basically it's the Z component of the whatever the previous pulse was right after we did it. And then that one is decayed by this time here. So this is the TR again. Because we're interested in this point A, it's going to be e to the minus whatever the TR time is over T1, that much decay. Okay, so that's just the Bloch, we just wrote out the Bloch equation again exactly. So now, now assume that we did a small flip. So this was, yeah, this is A up here. So this is, use Bloch. So now, assume small flip. So that's going to be this cosine, because that's the cosine is the one that's describing our longitudinal z-axis magnetization. And so if we assume a small flip, then our magnetization z of the nth pulse, is that right? Make sure I got that. Yeah. It's going to be mz 0 1 minus, just exactly the same thing for T1. And we're going to have z n minus 1 times the cosine. So what that's saying is we take whatever the mz was right before the n minus 1th pulse, that's the 0 minus here, and so that guy is over here, so that's mz of the n minus 1 pulse right before it, and multiply it by the cosine, and that's going to tell us what our starting magnetization should be. So, and then finally multiplied by e to the minus tr over t1. Okay, so now we've sort of made a little bit more of a mess, but this is a little trick, sort of mathematical trick. Let's just assume we're in equilibrium. So now empirically we know, like, if you do this pulse sequence, you still get a signal after 10 seconds of doing it, and so you and that signal is pretty stationary, and so we know empirically that actually occurs. We could have more mathematical arguments, but just assume that we're in equilibrium. And what does that mean? So what that means is that whatever the magnetization was, the previous case, this case right here, right before we did the flip, is going to be the same as the magnetization of the next pulse. So writing that out would be, so the mz of the current pulse right before we did it, we're just assuming that that's the same as what the magnetization was before we did the n minus 1th pulse. So we're just assuming that. And we'll call that the magnetization Z steady state right before the pulse. So we're just assuming that this is, we assume that we're in equilibrium. So this is our assumption. Okay, so now we can sort of simplify this one, because what are these two guys up here? Well, so here's one of them up here, and then here's the other one up here. And so So what we do is we say, well, we've just assumed that those are the same. Okay, so let me just like stick that guy in there and stick that guy in there. So if we just assume they're the same, then we can basically just substitute that in there and solve for this guy. So basically, just substitute, mz steady state in, solve for it. Because here it's on both sides of the equation. Solve for it. So you should just work that out to make sure that what we get, so you can see how we got what we got. So if we just basically, solve for our assumed equivalent magnetization Z steady state, what do we get? So we get magnetization steady state, Z steady state right before the pulse is going to equal mz0 times that first Bloch equation, e to the minus tr over t1, and then that whole thing over 1 minus the cosine of the flip angle times e to the minus tr over t1 again. Okay, so that was, use the Bloch equation, assume we've got a small flip, assume that we're in an equilibrium, solve for this guy, but then we're going to still have some decay. And so what is that decay? That decay is our echo time. And so our echo time, I should put that in here. So here's our TE, and that might be, 3 milliseconds. Hardly any shorter than the TR. And so then we're going to have to stick it into the Bloch solution for T2, and what is that? That's just multiplied by e to the minus TE over T2. So our bottom line then is going to be this is like allow T to decay from TE, because we didn't record the signal. This was just the signal right before the transverse, right before. So after pulse, magnetization longitudinal goes to transverse. And so here's the amount, that's the steady state. We just assumed that these two things were equal, and so there's the steady state number of longitudinal. And then what we're going to do is turn that into the pulse. We'll turn that into transverse. And then we turn it into transverse and then allow it to decay. And what is that? That just means substitute whatever we got into the Bloch equation solution for T2. And so our final answer is the MXY magnetization, because we turned it into transverse at time TE. So that's time TE is going to equal this guy up here, and times 1 minus C to the minus TR over T1 divided by what we had before, 1 minus cosine of the flip angle times e to the minus TR over T1 again. and then that whole thing multiplied by the sine of the flip angle. And why is that? Well, it's because you want to know like this amount of transverse magnetization, because it's not a 90, so it's going to be less, multiplied by the sine, and then decayed by the echo time over T2 star. So that's the final answer. And so now we have to sort of like see how this equation behaves. And so what are the main parts of it again? So we've basically got, you know, three unknown tissue properties, three unknowns. These are tissue properties. And what are they? Well, there's the the T1 value. That's one. And then there's the T2 star value. We don't know what that is. And then there's the proton density. So those are the three unknowns. And now we've got three knobs. So these are three knobs on the scanner that we can change. And what those are, we can change the TR, and we can change the TE, and we can change the flip angle. And it turns out the flip angle is the one that makes the most difference. So, and then finally, one data point. So we're highly underdetermined. So these things we can control, and we know what the scanner setting is. And then we've got three tissue properties that are affecting the signal, and we're just collecting one data point, so we're highly underdetermined to sort of relate that data point to tissue type, because it completely depends on what the value of the other ones are. And so what we want to do now is just sort of plot this equation. So you could just stick that equation into MATLAB and just, it's not that hard of an equation, and just plot it and just see how it behaves. And so that's what we want to do for assumed numbers of T1, T2, and proton density for, say, gray and white matter. So we often want to distinguish gray and white matter. So let's just plot out what the signal looks like as a function now of flip angle. So this is flip angle. So everything else held constant except for the flip angle. So just change the flip angle. It turns out the flip angle is the thing that most strongly affects what the contrast between two tissue types is. And so with this kind of a sequence. So if we plot out the gray matter, so I'll do it in green. So here's that equation plotted out for, so this is gray matter. So if we just plug in a number for the proton density of gray matter and the typical T1 of gray matter and the typical T2 of gray matter, and then see what happens. So those are all fixed. And then see what happens, and then also fix the TR and the TE. So just pick a TR. So just pick a TR, TE, and so that we can just get our two-dimensional graph. So now we're just changing the flip angle, and we're just looking at the amplitude of the signal. So this is just the amplitude of echo. So what's the amplitude of the signal? And so you get a curve that looks like that. And what is this is like, say, about 10 degrees, something like, that's approximately where it is. So now what happens if we do the same plot, except pick TE, and then, insert proton density T1, T2 for gray matter, and then separately white matter. So what do we get then? We get a different curve. Looks something like this. It's kind of got the same shape. So that's the signal amplitude as a function of flip angle for white matter. So obviously we don't want to do a big flip, so if we get out toward 90, we sort of get almost nothing, because we're stamping out all the longitudinal magnetization, and it takes forever for it to recover, and so there'll be a little signal, but it's really small. So this guy should still be above there. And so what is our bottom line? Well, what we would like to do, we have to sort of like pick a flip angle. And so it turns out if we pick a flip angle that happens to be right here, disaster. Because that would mean that gray and white matter are exactly equivalent if we happen to pick that flip angle. And so what we really want is like, what is the difference? What's the difference between these two signals? That's what we really want. And we could actually, you could plot that in MATLAB. You could just say, write an equation for the gray matter, write an equation for the white matter, and then just subtract them and make a third equation. That's the subtraction of them. And so what happens if you say like white matter versus gray matter? You'll get something that would look, say, something like this. So this would be, white matter minus gray matter. And really what we want, it's a little bigger over here, what we want is the maximum of that guy. Right, so we want this right there. What is the biggest contrast between the gray and the white matter? And so, and it's quite, and again, this is like, you're on the scanner and you're going like, I did an 8-degree flip. That seemed pretty good. Let's try like a 9-degree flip. And you go, whoa, that doesn't look good at all. There's no difference between the gray and the white matter at all. And then what if I try like a 5-degree flip? Oh, I just made gray matter brighter than white matter. So that's the value of sort of knowing this equation, where it comes from. And so all we're doing is we're just taking this equation. It's got 7 parts in it. It's got the data. That's what we're plotting on the y-axis. It's got 3 scanner parameters and then 3 tissue parameters. And then we're multiplying it by making 2 copies of that equation with 7 parts so that we can have an equation that shows us flip angle for white matter versus gray matter. And then what we really want is what's the optimal setting to give us the most contrast between the gray and the white matter, and also to tell us whether the gray matter is going to be brighter than the white matter or darker than the white matter. So it's a relatively simple argument, but you come to a sort of a completely different kind of parameter that's actually controlling what the contrast of the tissue is. Okay, so any questions about that? So we start off, just use the Bloch equation. We assume we've got a small flip, which gives us the cosine. Then we just declare we're in equilibrium, so those before the previous pulse and before the current pulse are the same. Then we can substitute that same thing into this equation and then solve for it to get it all on one side. And then we get this, and then we have to sort of like allow the signal to decay because we don't record the data instantly after the RF pulse. There's going to be some echo time, TE, and so that's where the sine comes from. So this is basically the equation for, fast gradient echo, fast spoiled gradient echo. We didn't mention spoiling, yeah. So what's the spoiling? The spoiling means we've got some magnetization left over and we got to spoil it or crush it. Spoil, crush, that's kind of synonyms. So spoil or crush it. So there's some extra parts of the pulse sequence I didn't draw to try to get rid of any. So like, kill MT before next pulse. And this derivation relies on this. It assumes that you've got no transverse when you start, and the transverse only comes from whatever the longitudinal was. Of course, there is some transverse, but that's why we spoiled it. So that's why it's spoiled grass. Okay, any questions about this? I went over it pretty slow and clearer than last year. Okay, so now let's talk. So that was the first fast gradient echo, flash, spoiled. It's spoiled grass. So now let's talk about something that's it's pretty simple and straightforward, which is but it's very critical for when you're recording data, which is what are the factors that control the signal to noise of your image. And normally you don't really think about signal to noise. You're just looking at an image. You don't really sort of think about signal to noise, but it's totally critical. If the signal to noise is very low, then your image just looks like crap. It just looks like a mess. It will just be all speckly and you can't sort of see anything. And if the signal to noise is very low, you literally can't see anything. It just looks like random speckling of gray and white. And it's actually quite easy. You can just tweak the scanner parameters and end up with a completely useless image that you can barely see. So first of all, what is the signal to noise? There's a lot of different signal to noises. There might be signal to noise over time. Here we're just talking, what we're defining the signal to noise, ratio. So we're defining it as, and then we're going to write an equation for it over here, but here's the definition of what we mean by it. And so what we typically mean by it is go to some part of the image that is actually a real object and average some of the signal from that part of the image across space, and then divide it by the standard deviation of the noise. So it's very common to divide by the standard, that's a good thing to do, divide by the standard deviation of something to sort of determine how big a signal is, because if you've got a really big standard deviation here, you're not going to have a very good signal to noise. because it's in the denominator. But what is it, how would you practically measure that? So this thing, this thing means the average. So you would just take an image. So here's an image of a brain. And then take a little chunk of the brain. So here's a little chunk of the brain. And if you blow that up, what does that look like? Well, it's a bunch of voxels of the brain, like that. And then take a little chunk of the air. That's noise. Because there's no signal coming out of the air, or there's hardly any protons in the air. You can sort of consider that it's, and then, do the same thing with that. And so if we take that guy, what we can do is we can sort of calculate a standard deviation. So we can calculate, a sigma for that guy. And then this guy, we just average. So calculate the standard deviation across the voxels that came from something that's not an object, not a signal generating thing, the air, and then just average the brightness of this. So average the brightness here, calculate the standard deviation across space here. That's what we mean by our signal to noise. And we can talk about signal to noise over time. It's a separate thing. If you read in the notes, you can see other kinds of things to other kinds of signal to noises to calculate. But here we're just talking about sort of signal to noise in a spatial sense. And like I said, if the signal to noise is bad, what will happen is the image will sort of kind of gray out with speckly stuff, and if it's really bad, you can't even see where the brain is. So what is the equation that describes, we won't derive it at all, but what is the equation that describes the, signal to noise ratio per voxel, or per pixel in the image? And it's proportional to the following. And so the most important thing here is the voxel size. So this is the voxel size. And notice the X, Y, and Z is all in there. So this is the voxel size. So voxel size is overwhelmingly important for signal to noise. And just to sort of, we're not done with the equation yet, but we just talked about the voxel size first. So, let's just examine like sort of a 2 by 2 by 2. We do a 2 by 2 by 2 scan. That's 8 cubic millimeters for a voxel. And then we do a 3 by 3 by 3 scan. And that's 27 cubic millimeters for a voxel. So that means that the signal to noise of the 3 by 3 by 3 scan is 3 times the signal to noise of the 2 by 2 by 2. So this is a very important thing. So with slight changes in your resolution of your scan massively affect the signal to noise. Now, you can improve the signal to noise by just collecting more scans. It's intuitive. You do one scan, it looks kind of noisy, collect like a second scan, third scan, average them all together, you're going to get a better signal to noise. But unfortunately, that number is under a square root sign. So this is the number of acquisitions. So if you just do one acquisition, you'll get a certain signal to noise. If you do 2 acquisitions, what's going to happen? You're going to get a square root of 2 improvement in the signal to noise. So just compare 1 to 2. So 1, the square root of 1 equals 1. 2, the square root of 2 equals about 1.4. So that means if you do a second acquisition, so this is reps. So repetitions. So if you just do a second acquisition, you do 1.4 times better, not twice as good. So let's go back to this one right here. How many repetitions would we have to do of 2 by 2 by 2 to get the same signal to noise as 3 by 3 by 3? So if you just use this equation here, what do we have to stick in here to cancel out, going from 2 by 2 by 2, to cancel out going from 3 by 3 by 3 to 2 by 2 by 2. So that's about a factor of 3, and so we're going to have to put 9 in there. So that's the bad news. So 9 acquisitions at 2 by 2 by 2 has the same signal to noise as 1 acquisition at 3 by 3 by 3. So the voxel size is overwhelmingly important because it's outside of the square root sign in this signal to noise. So what are other things in here? Another thing that's in here is just the number of, this is another one that's very counterintuitive. It's the number of voxels in the XYZ direction. And if you increase the number of voxels, you increase the signal to noise. Very counterintuitive. So let's just take an example. So say we have a brain here. Looks like this. And let's do some voxels, okay? Let's make them like that. They're smaller than this, but we'll just make, just for illustration's sake, we'll just do that. Okay, so that's how many voxels. That would be n, x, and y. And now let's just do the same thing, except collect more voxels of air. So here's the same size brain, but we just made a bigger field of view, and we collected the same size voxels as we did before. So exactly the same size, just collected more of them. We didn't change the voxel size at all. Signal to noise is better. So why does our signal to noise get better when we just collect more data from the air? It doesn't sort of make sense at first. And that will help us a little bit in this case, right? Because if we're recording 2 by 2 by 2, typically we'll record more voxels, and so that'll help us a little bit. It won't be quite as bad as if we just recorded the exact same number of voxels as we did at 3 by 3 by 3. But the reason for this goes back to our equations, the equations about the signal. What is the signal in MRI? It's coming from the entire, every single data point comes from the entire brain. And so what happens when you record more air is you're actually recording more brain too, because every data point, which is basically equivalent to every voxel, you have the same number of voxels as you do data points effectively, you've recorded more data. It's kind of like a repetition in a way. So because every data point comes from the entire head, even when we record air, we're actually recording head. So this one is quite counterintuitive. You would say, like, you look at the scanner and you figure just make a bigger field of view, same voxel size. It seems like it wouldn't cause anything to get any better, but it does. But unfortunately, it's under the square root sign. So this is the number of pixels, number of voxels. So whenever we record a larger number of voxels, that's always good. And then the last one is the bandwidth. And this one is also one that's highly confusing. So this guy is is 1 over the bandwidth. And what is the bandwidth? You can either put 1 over the bandwidth there or just delta t. And what that delta t is, it's basically so here's like the echo coming up like this, gradient echo, for instance. And what we're doing is we're just recording samples of that. I'm spacing them further. There might be 256, but I'm spacing them further apart just for make a nice picture. And this distance between when we record a time point it's just like the speed of the recording of the data. And that turns out to affect the signal to noise. And, again, it's like, what's going on here? I mean, I remember, the MRI physicist telling me, it's just this is what you expect from the bandwidth. I go like, well, what's the bandwidth? It's the recording rate. How does that affect things? And the way it affects things is if you're digitizing something, so say you've got a signal like this, and we're digitizing it. What does that mean? That means we're taking instantaneous samples of it. So say I digitize it like kind of slow, like this. If I do that, I'm not going to characterize that signal very well. Let me just make another one that's a little bit even faster. So say we've got some high frequency signal in there like that. And say we just digitize it something like that. So we get a sample here, a sample here, sample here, sample here, sample here. So this is our estimate of the signal. It's not a very good estimate of the signal. All different kinds of things can go wrong. And so what we typically do, we either have to digitize faster, so there's two chances. So you could digitize faster, but a lot of times there's a constraint on that, or we could filter too high frequencies. And what do we have to do? We have to filter out any frequency that's more than 1/2 of our digitizing rate. And why is that? Well, if we're going about twice as fast as the highest frequency, then we have a chance of catching the up and downs of that frequency. If we're less than twice the highest frequency, then we're going to end up with an artifactual signal. And we'll talk about that more. And so what happens is before you actually record the signal, you have to filter it. So we have to sort of filter it. And so this is, filter out too high freaks before we, too high frequencies before digitize, before record, before sample. And so what happens then is the rate at which we record the data affects our filter. And so if we have a slower rate of recording, we've got to, so this is frequency this way. So what we have to do is we have to stamp down some of the frequencies more, these too high frequencies. If we spread out our time of recording, the individual points, we're going to have to filter out more. And when we do that, we filter out noise. So there's some noise here. So we filtered out more noise. And so what that means is a lower bandwidth, so lower bandwidth, meaning just the width of this filter, equals larger larger delta t, larger time between recording points, is better signal to noise. And a higher bandwidth, which means record the data more quickly, then we have to open up our filter and let in more noise and signal too. And so it turns out if you record slower, you get better data also. It's under the square root, so it's not as huge of effect as voxels, but That's the last thing that mainly affects the signal to noise. And you can change that on the scanner. You can set the bandwidth. You can just set what the recording rate is. That's a number you can program into the scanner. Those are the things that mainly affect signal to noise of your image. And what is it? It's the voxel size, how big the voxel is. That's the biggest effect by far. That blows the other guys out of the water because it's not under the square root. And then the other thing, but you can collect more data. That's always good. Collect more voxels, which is another way of collecting more data. Or you can fiddle with the bandwidth, which is like your data rate. So this is, rate of sampling. Sampling equals 1 over the bandwidth. And so if you sample faster, you're going to have to open up your filter. So these guys are low pass filters. Low pass, because that's 0 frequency. Low pass filter. Low, meaning it lets through low and filters out high. Okay, so this one is quite counterintuitive. A lot of people don't realize how much of a signal to noise hit you take by changing the voxel size, and then they also don't realize how do we get better signal to noise by scanning more air. But it's basically the same. It's basically the same kind of it's basically a repetition. You can think of it as a repetition because every data point comes from the entire head and the air. Okay. So this was actually one of the few useful things I've told you in the course. This one is worth remembering. So our basic sort of signal to noise equation. Is there any final questions in the last negative 10 minutes? All good out there? Okay, we'll see you guys on Monday.